Tonight on Nova Science Now. It wasn't easy.
No.
In fact, it took two mathematician brothers from Brooklyn, plus their supercomputer running 7.7 quadrillion calculations to solve a problem that looked like it was going to be a piece of cake.
And unfortunately...
Tonight, David and Gregory Chetnovsky solve the mystery of the breathing unicorn.
The petunia was a big puzzle.
Geneticists took an ordinary purple petunia and wanted to make it purpler. But when they tried, they got
the complete opposite of what we had expected.
No purple. Why? The answer to this riddle is so astounding it may lead to treatments for major diseases.
You've just listed cancer and HIV. These are famous, big, fat diseases.
Arthritis.
Well, stop listing them and tell me.
Are all these diseases affected by this one discovery?
Certainly they are.
The dream, of course, is to create a car with an engine so clean you could drink the exhaust.
Look it, he's dead.
Because the exhaust
is water.
But how close are we really to an affordable hydrogen fuel cell car?
I yearn for you, Robert.
You yearn for me, but...
Well, after a short and picturesque chemistry lesson from Public Radio's Car Guys, you decide. Hi, I'm Robert Krulwich, and welcome to Nova Science Now, where we consider not one, but several science stories. Tonight, they're basically puzzles, beginning with a problem. So just come on back, and... All right, stop. Good. The internal combustion engine, which fouls the air and uses gas, which comes from oil, which is getting expensive, involves the Middle East, gets us into all kinds of fights. Who wouldn't want to replace this with a more efficient and affordable alternative? But is there an alternative? Because there is this engine we keep hearing about, which is supposed to be fabulous. It's coming soon. But the puzzle is, how soon? Every year, Detroit unveils, with much to do, a car of the future. And the hoopla here isn't about what this car does, it's about what this car doesn't do. This car doesn't use gasoline, none, because it is powered by a fuel cell.
Fuel cells.
Fuel cells.
Powered by a fuel cell. Fuel cells are the wave of the future.
The wave of the future.
Really? This is the future? Well, maybe we should take a closer look. So I decided to test drive a fuel cell car, and I invited a couple of friends to come along.
What do we think?
We don't know anything.
Tom and Ray Magliazzi, the Car Talk guys from National Public Radio.
Well, it's that whistling noise.
Yeah, what is that whistling?
What's that about?
That sounds like F above middle C. I would like to open the hood just to see what's there. Don't shut it off.
Oh, yeah. And don't lock the keys. I'll leave a window open. Dying to see what's
What the heck is this? See? I knew it. It's not an engine.
Well, it has a box, and it has lots of things connected to it.
Yeah, my intuition tells me this is an electric motor.
So this is basically an electric
So the
motor.
electricity
You know
is
what
kind
it sounds like? It sounds like my Nord's refrigerator.
Tom and Ray know a lot about regular cars, the ones with internal combustion engines. This, on the other hand, is an electric car, but you don't plug it in. Instead, it's powered by this mysterious fuel cell thing.
Yeah, this is technology that none of us understand.
No one told us this.
Do we need help?
We need help.
Yeah, maybe we should
We
just
need
ask...
someone, a passerby. I mean, just some ordinary citizen.
Dan? Oh, my God.
Thank goodness the car comes with its own expert, Dan Kelly, who works for a company that actually makes fuel cells.
So it has an electric motor. What runs the motor?
All the electricity comes from the fuel cell. And the fuel cell is really made up of a collection of these.
This is a fuel cell? It looks like a black plastic license plate.
This is one cell, and it's like a sandwich. You just stack them up. You want more power? Add more cells. Make a bigger sandwich. And what goes through, if you look at it...
It's a piece of plastic.
And the grooves that are in it...
Yeah, what is this?
You get hydrogen runs through these grooves.
So what's really going on inside these little holes? How is this thing making electricity? Well, inside the fuel cell, there are two sets of tiny passageways separated by a membrane. And if you look very close, the two main sections are kind of like the two sides of a tennis court. On one side is hydrogen, and on the other side, oxygen. And then there's the membrane that separates them. It's kind of like a net. So here we are in a tennis court. Of course, you notice now, represent the atom oxygen. And for those of you who are oxygen atoms yourselves, you'll of course recognize that I have 8 electrons. This is a fuel cell, so oxygen is opposite hydrogen. There are 2 hydrogen atoms, and if you rotate, please, you will see that they too each have 1 electron. Now, it is in the nature of this kind of chemistry that hydrogen and oxygen are attracted to each other.
I yearn for you, Robert.
You yearn for me, but there is a membrane between us. Now, the rules of the fuel cell are, you will try to come to me, but you'll have to go under or through the membrane. Let's try under the membrane.
Try under.
So down they go, the 2 hydrogen atoms approaching the oxygen atom with ardor. But notice now,
Robert, I love you.
yes, through the membrane.
We made it. Oh, my God.
Now, but, and I use the word but advisedly, could you please rotate, so show the audience your butts at this moment. You'll notice that this has got no electron here. The question has to be asked, where are the electrons? Remember when the hydrogen had to come through the membrane? Well, when it did that, its electrons were stripped off. Electrons simply aren't allowed through the membrane in a fuel cell. But they do want to come to the other side, so very cleverly they go around the membrane, right at the edge of the fuel cell, over and over and over again. And moving electrons, well, that's electrical current. That's what lights up a light bulb, or in this case, what powers your car. And here's what makes the fuel cells so clean. After the electrons get to the other side, they rejoin their old friends, hook up with the oxygen, and before you know it, you've got H2O, water. Pretty neat. So in these cars, when you check the tailpipe, instead of exhaust, what you get
is water.
Oh, how do you know?
Because it looks like water.
Take a drink. Lick it. He's dead. I didn't like him anyway.
The very idea that a car's motor could be this clean has an enormous appeal, especially to certain politicians. They act like it's going to be easy. Well, sometimes they do. But as it turns out, there's a catch. Actually, a bunch of catches. Fuel cells are still very expensive to make. They wear out more quickly. And oh yeah, there's one other thing.
A fuel cell needs fuel. So we've been talking about hydrogen and oxygen as our fuel. There's lots of oxygen, but where are we going to get the hydrogen in the first place?
MIT chemistry professor Dan Nocera says, remember, you've got to have pure hydrogen all by itself on one side of the membrane to get things going. So where do you get pure hydrogen? Well, there's plenty of hydrogen on Earth. It's just not pure. It's stuck to other stuff, like oxygen, in water, of course. And hydrogen can be found in fuels like natural gas, hydrocarbons. But if you take it out of there, and that's where most hydrogen comes from today, you do get a waste product, carbon dioxide. And that's one of the bad guys in global warming. So what's the answer?
I think water is the key for the future.
Every high school chemistry student knows how to split water into hydrogen and oxygen. You just run electricity through it. That's electrolysis. But hydrogen and oxygen are so cozy and comfortable together, you use up so much electricity prying them apart, it could cost a fortune. So we are facing a significant technical problem here. How do we find a cheap, clean source of hydrogen? Oh, and there is another issue.
Excuse us for a minute.
Right back.
Yeah.
Don't we worry a little bit about the danger problem?
What about the Hindenburg?
Yeah, what about the huge balloon, the Germans?
Yeah, all the humanity, the whole thing.
Yeah. We got to ask.
Yeah, come on.
Dan.
What about the Hindenburg?
What about the
Remember
Hindenburg?
the Hindenburg?
Yeah, the Hindenburg.
The Hindenburg pretty much ruined hydrogen's reputation. But after the explosion, the fire here, the continuous flames that you see, some say they came from the canvas blimp, which was coated with highly flammable shellac.
Are you comfortable getting back in now?
Not really, no, I'll be walking back.
One moment.
Of course, gasoline is flammable too, and we drive around with gallons of that in our cars. It's something else about hydrogen.
Well, hydrogen's a gas.
Okay.
That means that most of the space between the hydrogen molecules is not useful to make energy. There's nothing there.
So, says Nate Lewis, a scientist at Caltech, getting enough hydrogen into a car is a challenge because it likes to spread out, and you've got to squeeze a lot of it into a small space. You can't use an ordinary gas tank to hold it because it would burst open, and you wouldn't want that.
Did I run stop sign?
No.
So the hydrogen tanks have to be super strong to hold hydrogen squeezed in at pressures up to 5 to 10,000 pounds per square inch. But even with that special tank, it's tough to get enough hydrogen in the car. For instance, to drive 300 miles, you might need a gas tank 4 times the size of the one you've got now. Which leads Professor Lewis to suggest the best place for hydrogen fuel might be in power stations to light up cities and factories. After all, why rush to put this fuel out on the road when you can easily store plenty of it in a factory basement?
So you're a put it in the basement guy.
Put it in the basement first. And then, if we ever figure out how to use it to move us around, that would be great. But your car is the last place that you want to put hydrogen.
But the dream of a car that spews out nothing but water is so appealing. And if we could use water to fuel the car, that would be even better.
When the technology is really there, you'll be able to open that little gas fill and fill it up with water, like my brother used to do when he was a kid.
Yeah, so the car will run.
But the technology to get hydrogen from water efficiently and affordably, that technology doesn't exist yet.
Well, is there anything that we know of that does this regularly, that breaks apart water and...
We do. It's the leaf.
The what?
Leaf.
The leaf?
It turns out the leaf is a pro at splitting water. In photosynthesis, leaves take water and break it down. The oxygen goes into the air, thank goodness, because that's what we breathe. And the hydrogen hooks up with carbon to make carbohydrates, which the plant needs for fuel. And the energy to do all this comes from the sun. So does Dan Nocera want to make like a leaf?
And so what we've been doing is trying to actually not duplicate what a leaf does, but we're saying, can we generate hydrogen and oxygen by entirely new ways?
In his lab, lasers stand in for the sun.
What we do is we bring this laser beam in, and now you see actually here's a compound that's capturing that green light.
So this is your version of sunshine, and this is your version of something that sunshine is acting on.
The laser shoots through a liquid mixture concocted in Nocera's lab. He's trying to design a chemical, something like this pink pea pod thing, that does a special trick. So when light hits it, it will pull apart the H from the O.
Have you ever taken a droplet of water and found a way to just release hydrogen?
We haven't done water, but we've done hydrochloric acid, and we've been able to make hydrogen.
So you once got...
So that's a no. But there are labs all over the country now working on hydrogen. Some work with algae, some with solar collectors, and these guys are making hydrogen from water and sunlight, but at least for now, it's very expensive. And just last year, the National Academy of Engineering and the National Research Council reported there are major hurdles on the path to a hydrogen economy, and that clearing them will not be simple. So, even though the president is saying we could have hydrogen cars for today's generation,
the first car driven by a child born today could be powered by hydrogen and pollution-free.
If the car's really going to be pollution-free, the hydrogen in the tank will have to come from a clean source. And so far, when it comes to splitting water, we're way behind the leaf. Dan and other scientists are trying to catch up, and will keep trying. But the secret, he thinks, may be very subtle. So how long did it take for the leaf to figure out how to separate hydrogen from oxygen?
That took between 2 and 4 billion years.
But how much time do you have?
I'm guessing around 20 more years.
And so, whatever the politicians may say, learning to make like a leaf could take a while.
Okay, so we do have time then for a very short puzzle. This one lasts 50 seconds exactly, unless, of course, you happen to guess the answer earlier.
The key ingredient of this substance was originally extracted from the sapodilla tree. Nowadays, the formulation is coated with fine particles of sucrose and enclosed by a thin layer of aluminium 7 microns thick. It contains synthetic materials blended with natural products such as Lecky Caspi and Masaranduba. On contact with the enzyme amylase, secreted by glands in the buccal cavity, its texture is transformed to a malleable compound with elastic properties. After several minutes grinding in a heterodont interface, oral fatigue often leads to removal of the sticky molecular structure and adhesion to a suitable surface.
Well, if you got that one, we do have another one at the end of the program. It involves a filter-feeding sedentary metazoan, but we think you'd probably want to stick around for that. Whenever a museum wants to really examine a masterpiece, get in close enough to see the hidden details, the brush strokes, the really teeniest of gestures, what they can do is they can divide the painting into imaginary squares, small squares, and then they can take detailed digital photographs of each segment. And then they can patch all the photos together into an exquisitely detailed whole for scholars all over the world to study. This isn't hard, it's actually kind of easy. But suppose instead of a painting, suppose you're photographing a unicorn stitched out of thousands and thousands of fibers. We're talking here about a tapestry. Now, to put the unicorn pictures back together is a puzzle of such enormous difficulty you would need a supercomputer to do this right, and not just a supercomputer. You'd need a couple of guys we know in Brooklyn. Correspondent Chad Cohen reports.
And of course, we cannot go back to just one bit. And another is to have 2 bits at a time. It will be definitely at least 50% more significant.
The sound of equations blends with the hum of New York City traffic as these two world-class mathematicians make their way to their lab at the Brooklyn Polytechnic University. Gregory and David Chudnovsky seem to have a never-ending conversation about their passion for numbers. It's been that way since their childhood days in Kiev, where younger brother Gregory developed myasthenia gravis, a crippling neuromuscular disease. David has always been there to help, and since emigrating from Ukraine in 1978, the pair have been inseparable.
No. Paper. Yeah, paper consists of already grains.
Between their math speak and Russian accents, conversation with the brothers can be a challenge. Thoughts come to them rapidly. So rapidly, they often complete each other's sentences.
Simply becomes nothing. You take a difference.
Nothing or a small distortion.
Their passion for the bigger, deeper meanings of numbers demanded the calculating power of a supercomputer. And since they could never put the millions of dollars together to buy one, they built one from mail-order parts.
It's a good advertisement for Home Depot because PVC pipe, $250 for 12 feet. Just little compute device.
Tom Morgan is their doctoral candidate.
You wake up one morning and we have a unicorn emergency. Well, the day before you're working on some study of mathematics, and the next morning you're working to try to correct a problem with a unicorn.
Yep, he did say unicorn. The unicorn tapestries, to be precise, the prized possessions of the famous Cloisters Museum in Manhattan. These 500-year-old fabrics are some of the most celebrated medieval art in the world. The masterfully woven interlace of wool, silk, and silver threads, tens of thousands of them in each tapestry, took years to complete. The artworks presented a mathematical challenge that would end up in the Chodnovsky's lab, and started a few years ago when all 6 of the priceless tapestries were taken down during a building renovation.
When the tapestries were removed from their galleries at the cloisters, they arrived in an unmarked truck here at the Metropolitan Museum. They were taken to a room in the basement known as the wet lab. You won't find it on any visitor's guide. There they were laid out to be cleaned and photographed.
The museum had just begun to use new digital photography to document its 2.5 million piece collection, and the giant tapestries demanded a special approach for the head of the Met Photo-Studio, Barbara Bridgers.
What we really wanted was for each individual digital file to reveal almost each and every thread.
So they built a special rig to suspend the camera over each tapestry and carefully scanned 3-foot by 3-foot sections that would be pieced together later. But there was an unexpected problem. The digital files were so enormous, none of the museum's computers could handle them. So they searched for a solution. 5 years later, enter the brothers Chodnovsky.
They called me and explained that in their spare time, for fun, I think, which is what great mathematicians do in their spare time, they thought it would be interesting to create a software program that would stitch image files together outside of any visual clues, based purely on the zeros and ones and the mathematics underlying the file.
The problem looked amazingly simple from a mathematical point of view.
Their challenge? To take the 30 tiles, 30 digital snapshots of the unicorn in captivity, and precisely stitch them together. For 2 talented mathematicians, piece of cake.
It was a technical challenge.
But you think that you really can walk over it, and in 2 weeks you help people, you had fun, you use hardware, and you walked out, and everybody feels good. And unfortunately...
It never works this way.
When they loaded the images into their supercomputer, something was very, very wrong. The tiles just wouldn't line up.
And here on this tile, it simply does not match. Yeah. But it's very peculiar, does not match, you know. Some pieces actually match, and some pieces don't. But this one does. Right. It's actually absolutely maddening.
Right, so you would think you just take this and move it over.
Right, but look at this flower. The flower is perfect.
So therein lies the rub. If you move this here, this flower's off.
It seems
so they said, this just is not working. And it's very clear to us from the numbers that someone has manipulated these files. And I said, no, you know, that's not the case.
What was the case was that the brothers' math did reveal some kind of motion in the tapestry. Perhaps the photo staff shifted the fabric accidentally. Or maybe the camera was jolted during the long exposures. So David and Gregory created a vector displacement map. That's these little arrows here, to track how the tapestry was moving.
As these were moving forward, the other pieces actually were moving in some places backwards. Right.
By examining the direction of 15,000 vector arrows, the brothers realized the motion had nothing to do with the photographers at all. The tapestry had moved all by itself. After centuries of hanging on a wall, when the 500-year-old threads were cleaned and placed on the floor, they started to relax and shift randomly. And it was all captured in the pictures.
It's basically like photographing a surface of a very slowly moving water. It's never the same. Right. And so you photographed one piece, and even if you photograph it, say, a week later, it would be totally different shape.
Right. Of course, this is the afterthought.
It's a good afterthought.
It's a good afterthought. Right? Initially, we got this.
Now they had a problem worthy of a supercomputer and a team of mathematicians. The brothers had to create what are called warping transformations. That's the kind of math that finds recognizable patterns among features which are similar but not identical. It's also used to solve problems in handwriting analysis and speech recognition. For the tapestries, it took a gigantic set of equations to optimize the position of every pixel, all 240 million of them.
You start to pull out heavier and heavier artillery, and at some point in there you just say, well, I'm not going to let this thing defeat me, and we're going to make this image one way or another.
Week after week, Team Chodnovsky fed subsets of the tapestry into the supercomputer, which had to perform some 300 million operations per pixel to digitally weave each thread back together.
However, it was a very interesting challenge, and it's a very damn complicated thing. Unfortunately, there is an issue of pride.
After 4 months of number crunching, the Chodnovskys entered the final instructions, and for 30 straight hours, the supercomputer ground out not a billion, not a trillion, but 7.7 quadrillion calculations. Finally, Unicorn in Captivity was reborn in digital form. It was flawless. A version of it now hangs in the Brooklyn Polytechnic Library, not far from the brothers' lab.
After they successfully put the one tapestry together, I said, well, there are 6 more. And they said, we're busy. We're booked.
Well, they didn't stay booked very long. This summer, the brothers will be working once again with the museum's photo team, most likely on this Vermeer painting. Their goal is to use mathematics, of course, to break down the pattern of brushstrokes, perhaps uncovering the sequence of how Vermeer laid them down. And with a little luck, maybe this time, the artwork will sit still.
Never happens. There will be something else. We don't know what, but there will be something else happening here. Otherwise, again, it will be too good to be true.
We know not to touch tapestries, but maybe after that we will know not to touch
paintings either.
Correspondent Chad Cohen. What if I told you that recently scientists made a discovery that's so surprising and so powerful? Not only are we about to know much, much more about how all these diseases work, Alzheimer's and asthma and arthritis and cancer and HIV and all the others, there's a chance, it's a real chance, that we can treat many of these diseases much more effectively, all because of this one discovery called RNAi. It was a little I at the end, which I'll explain later. You don't hear much about it, but RNAi is a really big deal. And the curious thing about it is the discovery of RNAi was an accident. It was a puzzle that appeared in a petunia. It was a purple petunia. But to fully appreciate this tale, let's back up a bit. Every creature, and you know this from high school, is made from a recipe that comes from its DNA, spelled out in chemicals, A's and C's and T's and G's, inside the famous double helix. Every creature has its own DNA, different for mice, and then for whales, and for flowers, but to go from a chemical recipe, A's, G's, and T's, to a real creature that squeaks, or soars through the air, or turns gloriously pink, that requires RNA. RNA is the thing that turns you from a chemical code to a real, pulsing, living creature. RNA builds life. That's big. So big that to RNA researchers like Greg Hannon, RNA is more important than DNA.
DNA really works for RNA, and proteins really work for RNA.
Would you get an argument, by the way, from somebody else?
Oh, undoubtedly, sure.
So how do you get from DNA to become a real creature? Well, let's take one of those fantastic voyages and we'll show you. We're going to find DNA and, well, we'll make it a typical cell, so we're going to have to fly in and then go off to the nucleus of the cell, which will make a beautiful castle, the headquarters. And there's the DNA, the master code, inside the nucleus. DNA, says Greg, never leaves the nucleus.
You ever meet one of those mean librarians, you know?
Yes.
Special reserve section?
The ones that go, pow.
Right. You can take the thing, you can copy it, but you can't take the book, because somebody else might need it.
So if DNA is locked in the nucleus, how do we get the information out to build our creature? Well, that's what RNA does. That scribe, copying recipes out of the cookbook and throwing them out the window, out to the cytoplasm C that makes up most of the cell, all those recipes floating through the air, they are RNA. And to finish up, in that sea, you see hundreds of thousands as well. We've made them into little guys with chef hats.
Those would be ribosomes, and in your world, there are chefs who are using the recipes that are written in the RNA.
And whenever a recipe lands on a chef, whatever it is, he cooks it.
Whatever it is, he cooks it.
And each recipe is for a protein. Proteins build cells, bone cells, brain cells, all cells. So all these chefs are basically building you. You are made of proteins. And because of RNA, we can copy, we can distribute, and we can cook up you and me. And RNA's been doing this for more than 3 billion years. But there was something spectacular about RNA that nobody knew till just a few years ago, and they learned about it, as we told you, by accident.
Here's a good one. Maybe this.
In 1986, geneticist Rich Jorgensen was working at a biotech startup company in California. He was asked to create a spectacularly dazzling flower.
That looks good.
To attract investors.
So that we could convince venture capitalists, investors, to give us more of the green stuff, more money.
Still, back in 1986, geneticists didn't know how to work that easily with, say, roses. And so
we began with a simple plant, regular garden variety petunias. Petunias being a plant that were easy to introduce genes to in 1986.
And so they decided to create a very, very, very purple petunia. Rich knew which gene produced purple. He knew how to sneak an extra copy of that gene into the plant's DNA, the master text, to be copied by that monk-like scribe.
It will be transcribed by the monk, the same as any other gene. And he'll throw the transcript out the window into the cytoplasm, where the chef will be able to pick it up and use it.
Rich thought that if he added more purple recipes, he'd get a purpler petunia. So he did it, and he waited. And what happened?
We produced, instead, white flowers.
White flowers?
Complete opposite of what we had expected. Completely white flowers. We lost pigmentation completely. Our initial reaction was that something must have been wrong with the gene that we had engineered to introduce to the plant.
A mistake?
A mistake. So we checked everything out, and there were no mistakes that we could find.
So why didn't the petunias turn purple? What happened?
The petunia was a big puzzle. Nobody understood why, when you add an extra gene for purple, you should not get more purple, but less purple. It took a decade of brilliant scientists working on petunias and fruit flies and worms and other organisms to finally work out what was going on.
And what was going on is, quite by accident, Rich had discovered a secret inside living cells. Cells from time immemorial have had a mortal enemy called the virus. So let's imagine that the virus is a pirate ship. It lands. It then sends invaders inside the cell to shower recipes down to those cooks. But some of those recipes, you'll notice, look a little different. And what's in these recipes is not good for the cell.
No, it's decidedly not good for the cell, because the sole purpose of that virus is to make additional copies of itself, and to the point that the entire cell is filled up with this, and the cell explodes, releasing these viruses to go and then infect whatever other cells they can find.
So the theory is that long ago, cells developed a secret defense system which we will call the COP. What the COP does is when viruses invade and create showers of murderous recipes, the COP looks and thinks, some of these have a very fishy shape. It's a chemical difference which comes down to some of the viral recipes are 2 pages instead of 1, and one side is a mirror image of the other. But the point is, to the COP, there's something not right about this shape. So when they see it in that shape,
they say virus.
And
they say, uh-oh.
And the COP destroys the recipe. And when you say it destroys, is this, should we think like a kung fu kind of thing? Is it like, sort of deal?
Yeah, a little enzymatically, a little thermodynamics.
Enzymatically?
Like that. Enzymatic kung fu, maybe, yeah.
The COP destroys not only the oddly shaped version, whenever he sees that recipe. Oddly shaped, regular shape, that recipe in any form must be destroyed to defeat the virus. And the interesting thing is, until 1998, nobody knew that cells had this defense mechanism.
We had no idea it was there. That's what's so amazing, is this whole mechanism had been sitting there where cells were able to tell that something was very funny when they saw mirror image messages and start not just destroying the messages, but destroying anything that looked like that message. They'd worked out this whole defense system against viral RNA, and we then accidentally stumbled into using it.
The accident was Rich Jorgensen's purple petunia. The question, remember, was when Rich tried to make his petunia more purple, why did it turn white? Well, the answer, it turns out, was that Rich, by accident, discovered the cop. When Rich invaded the petunia cell and inserted his make more purple instructions, he didn't know it, but his purple instructions happened to have that suspicious viral shape. So when the cop saw the recipe, the cop thought, virus, and destroyed every recipe for purple in the cell.
So there's no possibility anymore of producing the purple pigment because the purple transcripts are gone.
If there are no recipes for purple, the chefs don't cook purple.
And because there's no purple pigment produced, the flowers will be white.
And that's how Rich and his petunias helped discover what we now call RNAi.
RNAi means RNA interference, because the cop is interfering with RNA messages, with the recipes in the cell.
And when scientists realized that every plant and animal cell has RNAi, a way to turn off the recipes, turn off genes, they thought, maybe we can use these cops to work for us.
Okay, Chubber?
Which brings us to Marty Russell. 78 years old, she and her husband used to spend lots of time here at their daughter's nursery.
Thank you, Rosie.
Years ago, she enjoyed doing lots of things.
Her passion was reading.
Oh.
She would read everything.
Golf.
Yeah.
I love to play golf, bridge.
But then Marty began losing her sight.
Couldn't see, and I'd probably get the peppers in with the zucchinis, and there'll be big problems then.
So she went to her doctor, who told her,
You have macular degeneration.
a degenerative disease caused by too many blood vessels growing in the eye, underneath the retina.
As these blood vessels grow, they leak out fluid and blood in the center of her vision, and it's as if you're looking through a very dirty windshield, essentially.
I went home, I was just devastated.
So Marty volunteered to be a candidate for RNAi therapy, something so new she's kind of a pioneer.
She was probably one of the first to get it for any disease whatsoever, and specifically for macular degeneration. Hey, how are you?
Advertiser, how are you?
Good to see you. This is the VIP room.
I feel very honored.
The reason Marty has so many blood vessels growing in her eye, clouding her vision, is there's probably a mistake in her DNA, in a gene that produces too many recipes that say, make more blood vessels. So the chefs cook up proteins for more, and she ends up with too many blood vessels. Her doctor wants her to have fewer blood vessels. But how do you get the chefs to make fewer blood vessels?
Dude, it's pretty easy. You want to shut down a gene? Put in a copy of the gene with its mirror image. Signals the cell, better shut this thing down.
We inserted the needle after numbing her up.
So the doctors put literally injected RNA recipes into Marty's eyes that said, make more blood vessels. But they made those recipes look dangerous, like viral recipes, hoping the cop in Marty's cells would leap to it and destroy lots of recipes for more blood vessels, leaving Marty with fewer blood vessels. They wanted the cop to turn off Marty's disease. Did it work?
Marty's vision has improved. It's a very promising result.
I can play bridge now.
Which is very important.
I'm not great, but, it's part of my life.
She can see flowers again.
Oh, some of them are just gorgeous.
So apparently they did trick the cop in Marty's cells to reduce vein production, although not completely.
I see the yellow. Inside is just a little cloudy, but I can see it.
There's a lot of questions still that need to be answered. This is not a treatment that is as proven.
Can we deliver recipes to the right cells?
Lovely.
Does the treatment last?
That's beautiful.
All these are big questions. Still, in mice, RNAi has been effective with Huntington's disease, Lou Gehrig's disease, hepatitis, breast cancer. So, says Greg, if we ever work this out in humans...
any sort of disease that you can imagine becomes fair game.
All the diseases which would be helped if you shut off a gene.
Cancer, HIV, for example.
Wait, is this because you're just an RNA buff that you're saying? You've just listed cancer and HIV. These are famous, big, fat diseases.
Arthritis.
Well, stop listing them and tell me, is this a prejudice that you're telling me, or is this true? I mean, these are all candidates for this kind of therapy?
Certainly they are.
And finally, we have saved the best for last. The true power of RNAi goes even deeper than finding cures to terrible diseases. Because what RNAi does, remember, the cop's job is to turn off information, turn off genes.
The big problem of understanding, say, the human genome is you have 20,000 genes. How in the world are you supposed to know what each one does? Well, one very good way to start would be to turn off gene number 1 and see what went wrong.
So you could go through all the genes that make up a human, or for that matter, make up a petunia, and turn off each gene one at a time. If you trick the cop to turn off gene number 1, no color. So gene number 1 is involved in color production. Try gene number 2, no petals. Gene number 2 involved with petals, and so on.
You could make too many leaves. They could curl up. They could be upside down. Almost anything could happen.
But getting rid of the gene tells you what the gene does when it's working.
That's right.
The RNAi discovery is just amazing. 10 years ago, when we were sitting around talking about what would we really need to understand the human genome, we all said we would need some magic way that you could turn off any gene at will, just based on knowing its sequence. And what's happened is this discovery by scientists about RNAi has given us exactly that. It turns out that nature already had a way to turn off any gene at will.
And now, with RNAi as their key, scientists will have the means to decode every living thing, to identify the genes that allow us to grow, that allow us to move, that give us beauty and color. RNA is a modest little molecule, but what it gives us is the world. So now we go from the profound to the creepy. Imagine, if you will, a glacier. One of those vast mountains of ice that hang off of mountains or of coastlines. When you read about glaciers, they tell you that every year glaciers move. I mean, they don't sprint exactly. They just creep along at a rate of, well, we did look it up. And if this block of ice right here were a typical glacier, it would move about 10 inches every day. So if I'm standing, as I am right now, 20 inches from, let's make this an incoming glacier, in 2 days it would move from where it is now to here. So that's an average glacial speed. It's less than 1 foot every day. Now, here's the puzzle. We're going to take you to a real glacier. It's a big one that for some reason, says our correspondent Peter Standring, is behaving very badly.
Take a look around. This is Greenland's largest glacier, the Jakobshavn. It's more than 4 miles wide and over 1,000 feet thick. It looks solid and indestructible, but looks can be deceiving. Like any glacier, the Jakobshavn is actually a river of ice. It's moving. Fed by the massive Greenland ice sheet, it's now the fastest moving glacier in the world. Jay Zwally, a glaciologist from NASA, knows exactly how fast the ice is moving.
So right now, this ice is moving. You can't feel it moving. It's moving this far in 1 day. In a month, it'll be 5 feet past that pole over there.
Instead of moving 1 foot a day, which is normal for glaciers, in the last 5 years, the speed of the Jakobshavn has increased to an astounding 113 feet every day. And no one knows why. It's a mystery buried deep within the Arctic ice. Here you can see the consequence of all that speeding up, where the glacier meets the sea and enormous icebergs break off. This glacier is not just speeding up, it's shrinking. 8 miles in just the last 5 years as huge pieces of ice fall into the ocean.
To give you a better idea of just how much ice, take a look at this iceberg here. We're estimating it to be about 50 feet high. In terms of thickness, that's how much ice the Jakobshavn Glacier is losing each year.
The result is that this glacier alone is responsible for 4% of all sea level rise worldwide. So, why is this happening? At this research station set up on the Greenland ice sheet, scientists use a variety of tools to answer that question.
Hello there. How are we doing?
We keeping warm?
Yes.
Conrad Steffen is the camp's founder. He's spent the last 31 winters out on the Arctic ice.
And you guys manage to go about your business and your experiments without freezing to death out here?
Oh, I have never lost a grad student here on the ice.
About 10 miles from camp is this GPS receiver, which gives precise measurements of the position of the ice. This allows scientists to track changes in its speed and when they happen.
It's always exciting to take a look and turn the unit on and see what it's recorded throughout the year.
Around the clock, weather stations measure the height of the snowpack, the wind speed, humidity, and temperature. These instruments collect volumes of information, and here's where they put it all together. These red tents serve as both kitchen and laboratory.
Good morning. Good morning. I heard you have Starbucks here.
A warm place to ponder the mystery of what's happening to the Jakobshavn Glacier.
That's minus 5.8.
And is that Fahrenheit or Celsius?
That's all in Celsius. We measure everything in Celsius.
Connie Steffen says that the main culprit is rising temperatures.
The summer temperature have increased by about 1.5 to 2 degrees over the 15 years. But the winter temperature have increased by 6 degrees.
That temperature increase has led to a longer melt period, more days each year when the ice melts rather than freezes. Aerial and satellite observations show that the melt water, that blue area on the ice, doesn't stay on the surface. So, where does it go?
I know it's hard to imagine, but I'm actually standing at the bottom of a big lake. Measures 3 miles by 3 miles. By the end of July, enough of this ice and snow will have melted to fill this lake with 60 feet of water. Eventually, all of that water finds a hole and makes its way down to the bottom of the ice sheet.
Glaciologists thought that water would freeze before it ever made its way down through 4,000 feet of ice. And normally, it would, if it weren't for one thing. The incredible pressure caused by the huge volume of increased meltwater on the surface forces it to the bottom by sheer weight.
What people didn't know before was where that water went. They thought maybe it stayed in the glacier, thought maybe it went to the bottom, stayed in a tunnel. But our results show that it goes to the bottom and spreads out, actually lifts the glacier up a little bit and allows it to float partly on a bed of water.
Literally sliding it into the sea. And although this effect takes place mostly in the summer, recent satellite measurements show that even in the sub-zero Arctic winter, when there is no melt effect, the Jakobshavn is showing little signs of slowing down. Jay Zwally places the blame for this on global warming.
The really disturbing thing is the pace of things that have been happening in the last 10 years. Almost all the scientists in the world, all the respectable scientists, believe that man is having a definite impact. And we're seeing this more in the Arctic than anywhere else.
Just as unsettling is data from some of Greenland's other glaciers that show that they too are starting to undergo the same dramatic changes. Where and when, or even if this will stop, no one knows. But what scientists do know is that changes they once thought occurred over hundreds or thousands of years are today taking place right in front of their eyes.
Correspondent Peter Standring. Before we leave you tonight, we're going to offer you one last puzzle. We're thinking of an object which, like a glacier, is found in regions familiar to hydrographers, where it shows remarkable properties of both compression and evulsion. Can you guess what I'm thinking about?
Discrete spicules fuse together to form the skeleton of this organism. Its life revolves around pumping large volumes of fluid through the core tissue. Specialized flagellated cells drive the current in a single direction through a system of complex canals and chambers. Construction of these labyrinthine corridors can take years. It is a sedentary filter-feeding metazoan at home in the sea and in the bath.
Well, we're going to leave you now until our next episode, but Nova Science Now continues online. You can watch any part of this broadcast again. You can email your questions to scientists who are working on fuel cells, RNAi, glaciers. We also have a new section where we discuss and investigate new story ideas. We'd love your help there, so please, please tell us what you think about this broadcast. You can find us at pbs.org. I'm Robert Krulwich. Goodbye.
Nova is a production of WGBH Boston.